Howdy. This video is on electrochemical cells. By combining two half reactions in two separate beakers, creating a cell, we can actually convert chemical potential energy into electrical energy or electrical energy into chemical potential energy. Now, after watching this video, you should be able to recognize that potentials of half reactions cannot be determined independently and hence are defined relative to the standard half cell potential. If you remember, that's hydrogen ions plus 2 electrons going to hydrogen gas, and this potential for that half reaction has been defined as 0. You should be able to determine if reactions can be used as a voltaic or galvanic cell. I'll use voltaic and galvanic interchangeably, or an electrolytic cell. For voltaic and galvanic cells, we're converting chemical potential energy is converted into electrical energy. For electrolytic cell, electrical energy is converted into chemical potential energy. You should be able to recognize that chemistry is the same if one beaker or if 2 beakers is used. And so to create a battery out of solutions, you typically need 2 beakers to force the electrons to go through an external circuit. The chemistry in those 2 beakers is exactly the same as the chemistry in a single beaker. You should be able to describe how a cell and its components work. For instance, the salt bridge is used to maintain charge neutrality in the 2 beakers. You should be able to write and interpret cell notation. And so which reaction will occur spontaneous? We have zinc ions plus copper metal going to copper ions plus zinc metal, or copper ions plus zinc going to zinc ions plus copper metal. Now, if we look at that top reaction, we have zinc ions as reactant, and so we take the reduction potential of zinc, which is minus 0.76, and notice that we have to flip the reduction of the copper ions so we get the oxidation of the copper metal, and when we flip that half reaction, we get minus 0.34, and so the electric potential for that top reaction is minus 1.1. Now, the bottom reaction is just the top reaction switched, and so it's going to have the opposite sign, and so that would be plus 1.1 volt. And so for that top reaction, it's got a negative electric potential, so it's non-spontaneous, and so that would be electrolytic cell. We could actually force that reaction to occur by applying greater than 1.1 volt. For the bottom reaction, it has a positive potential, meaning it's a spontaneous process, and so we can actually use it as a voltaic or galvanic cell, converting chemical potential energy into electrical energy. And so it's really kind of cool. If we take a hunk of zinc and we put it in a solution out of copper ions, what should happen is we should get some of the zinc dissolving, forming zinc ions, and some of the copper ions plating out, forming copper metal.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown.
And so it's really kind of cool. We determine spontaneous, and spontaneous means occurs without any outside intervention, and that's exactly what happens. We put the zinc into a solution of copper, and so we form zinc ions and copper metal. Now, because all the electron transfers actually occurred on the surface of the zinc, there's no way we can harness that energy. And so if we want to get some of that electrical energy, what we have to do is we have to force the reactions to occur in 2 separate beakers and force the electrons to go between the 2 separate beakers. Now, again, the chemistry is exactly the same. We're using 2 beakers, but still copper ions will go to the copper metal, zinc ions will go to the zinc metal. The chemistry is exactly the same. We're just forcing the electrons to go through an outside circuit so we can take advantage of it.
Copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from...
And so it looks kind of complex, but again, the chemistry is exactly the same as if you're doing it in a single beaker. You're just forcing the electrons to go outside so you can actually use it to, say, light the light bulb. Now notice that the salt bridge is there to keep charge neutrality. And so if this battery started trying to work, then you'd have electrons going into the cathode compartment and you'd get a net negative charge, which isn't very stable. And so the salt bridge completes the circuit. I mentioned that all potentials are measured relative to the center half cell potential. You cannot measure a reduction potential by itself or oxidation potential by itself. Whenever you have a reduction potential reaction, you need an oxidation reaction and vice versa. So you cannot measure a half reaction potential by itself. And so we define the center half cell as having a zero potential and measure it relative to everything else. Now notice in this cell we have platinum as the electrode. The platinum is not participating in the reaction. It's just where the reaction occurs. And platinum is used because it's not very reactive. The oxidation potential for platinum is negative, and so typically it's not very reactive. It's in a group of metals that we call noble metals because they're not very reactive. But all these potentials are measured relative to the standard half cell potential. Standard half cell potential, again, is defined as zero. Now, typically you're given half reactions, reduction half reactions. I'm not sure why it's reduction instead of oxidation, but typically you're given reduction half reaction tables like these. And Leo goes Gur, lose electrons oxidation, gaining electrons reductions. And so notice that the electrons are reactants. And so these are all reduction potentials. Now to determine and so these are reduction potentials. Now if we swap products to reactants, we change the sign of the potential, and now we have oxidation potentials. Now there's two ways of actually determining the cell potential. One is by taking the reduction potential plus the oxidation potential, which is the way I prefer. Another way of doing it is taking the reduction potential at the cathode minus reduction potential at the anode. Now to me this is a little bit less intuitive, but they are exactly equivalent. And so the reduction potential at the anode is where the oxidation occurs. You can remember that because anode oxidation are vowels. Cathode is where the reduction occurs. You can remember that because cathode and reduction are consonants. And so anode is where the oxidation occurs, so minus reduction at the anode is actually equal to the oxidation potential. And so you can do E cell equals E reduction cathode minus E reduction anode, or you can do E cell equals E reduction cathode plus E oxidation anode. And again, oxidation's where the anode is where the oxidation occurs. And so I prefer the bottom way. In most textbooks and a lot of movies, you actually see the top way. And so that's why I want to make sure to clarify that. And so in all my slides, I always have the reduction potential plus the oxidation potential. And so here you see the zinc being oxidized. And so the 0.76 is the oxidation potential. Here you see the hydrogen ions being reduced. And so the 0.0 is actually the reduction potential. And so if we wanted to know what is the oxidation potential for the zinc, we can set up a zinc cell with the hydrogen cell and we just measure it. It's really kind of cool. The measured potential is equal to the cell potential as long as you're using standard conditions. And so as long as our zinc ion concentration is 1 mole per liter, our hydrogen ion concentration 1 mole per liter, and the hydrogen gas is 1 bar, then the measured potential should be equal to what we calculated using half reactions. Now when the concentrations change, then the potential will change.
Cell potential of a voltaic cell, such as this zinc hydrogen cell, can be thought of as the sum of two half cell potentials. Under standard conditions, the cell potential, E0, is the standard reduction potential of the cathode, minus the standard reduction potential of the anode. We can assign half cell potentials once we settle on a reference half cell potential. That has been chosen as the hydrogen half cell, with 1 molar aqueous hydrogen ion, and 1 atmosphere pressure of hydrogen gas. For the zinc hydrogen cell, the measured standard potential is 0.76 volts, and the standard half-cell potential for the cathodic half-cell is defined as 0. Thus, the standard half-cell potential for the anodic half-cell is minus 0.76 volts. This is the standard reduction potential for the reduction of zinc plus 2 ion.
And so again, please remember that reduction potential at the anode is equal to minus the oxidation potential. And so they're writing down the reduction potential at the anode as minus 76. I write down the oxidation as plus 0.76. And so oxidation always occurs at the anode, reduction always occurs at the cathode. And so during this reaction, it's actually kind of cool. You just look at the reaction, you see that the zinc electrode is actually getting lighter, and hydrogen gas is being produced.
As with all voltaic cells, the zinc-hydrogen cell consists of 2 half cells. On the left is the zinc-zinc ion half cell. It consists of a zinc electrode immersed in a 1 molar aqueous zinc nitrate solution. The hydrogen-hydrogen ion half cell consists of an electrode made from a non-reacting metal, such as platinum, over which hydrogen gas at 1 atmosphere pressure is passed. The electrode is immersed in a 1 molar solution of nitric acid. A salt bridge of sodium nitrate solution completes the electrical circuit. In this voltaic cell, the zinc electrode serves as the anode, the electrode at which oxidation occurs. The platinum electrode on the right serves as the cathode, the electrode at which reduction occurs. When the lamp is replaced by a voltmeter, the cell potential measures 0.76 volts. Electrons flow from the zinc anode through the voltmeter to the hydrogen electrode, which is the cathode. As in any voltaic cell, the anode is the negative electrode, and the cathode is the positive electrode. Zinc 2 ions are formed at the zinc electrode. At the same time, hydrogen ions are reduced to hydrogen gas at the platinum cathode. In this molecular level view, the hydrogen ions in solution are represented as the hydronium ions, the form in which the protons exist in solution. When a hydronium ion contacts the surface, an electron is transferred and a hydrogen atom is formed. The water molecule moves off into the solution. Hydrogen atoms formed on the surface migrate and eventually combine with another H atom to form molecular hydrogen, which bubbles from the surface.
And so kind of cool. And so again, we can measure potentials of half reactions by combining them with the standard half cell potential. Now we can look at these 2 reactions. So we have O2 plus 2H2 going to water, or 2 water plus O2 going to 2H2. Now we can actually just look at what's more stable. And so the water is actually more stable. And so you should say that the top one should be spontaneous and the bottom one should be non-spontaneous. You could also combine the potentials above and come to the same conclusion. Now the interesting question is, can we force this reaction to occur even though it's non-spontaneous? As long as we apply a potential greater than the absolute value of the minus 2.06, we can actually force this reaction to occur. And this would just be the electrolysis of water.
The decomposition of water is thermodynamically disfavored, but can be made to occur by electrolysis, the application of an external electric current. Here, platinum electrodes transfer electrons between 2 cell compartments to separate the decomposition products. Gaseous oxygen rises from the anode at the left, hydrogen from the cathode at the right.
And so looking at the reaction, you can see that you're forming 2 moles of H2 for every 1 mole of O2. And so the test tube on the right contains the hydrogen. It's got twice the volume as the test tube on the left, twice the volume of the gas. And so we can actually take a nice closest picture. In this case, the hydrogen's on the left. You can see there's more bubbles. And the oxygen was on the right. So in electrolysis, we're converting electrical energy into chemical potential energy. And so you can actually produce hydrogen gas and oxygen gas that way. It's important in industry. And so cells like these are sources for sodium hydroxide, for chlorine gas. It's also how aluminum metal is made efficiently. It's interesting, during Napoleon's time, aluminum metal was very scarce because it was very hard to convert aluminum oxide into aluminum metal. But when Hall developed this process, aluminum became much cheaper, and so now we use aluminum from everything from soda pop cans to airplanes. And so reactions that have positive potentials can be used for voltaic or galvanic cells. That means their delta G would be negative, the electron constant would be greater than 1. We call them product favored. If we plot the free energy versus reaction quotient, we get something like on the bottom. If you have a potential that has electric potential is negative, then it could be used for electrolytic cell. Its delta G naught would be positive. Electron constant would be less than 1. We call it reactant favored. And again, if we plot free energy versus reaction quotient, it'd be something like on the bottom. Galvanic cells or voltaic cells, again, I use those two terms interchangeably. We actually use to convert chemical potential energy into electrical energy. Oxidation at the anode, reduction at the cathode, that's for both. For electrolytic cells, we're converting electrical energy into chemical potential energy. The anode is labeled as positive for electrolytic cells. The anode is labeled as negative for galvanic or voltaic cells. Again, galvanic voltaic cells have to be based on spontaneous processes where E is positive, and the voltage produced is equal to E of the reaction. Now, if you're looking at standard conditions, that would be E standard. For electrolytic cells, they're based on non-spontaneous processes, and you have to apply a voltage a little bit greater than the absolute value of the standard potential. Now, it's kind of interesting. Your car battery is actually behaving like a galvanic cell. When you're starting your car, it's behaving like an electrolytic cell when you're driving your car. And so when you start your car, the battery is providing power to the starter motor. And so we're converting chemical potential energy into electrical energy. When you're driving your car, the alternator is actually converting electrical energy back into chemical potential energy. Now, the car battery is actually 6 galvanic cells connected in series. Each cell produces about 2 volts, and so together that's 12 volts.
A 12-volt automobile battery is actually made of 6 cells connected in series. Each cell produces about 2 volts by the reduction of lead dioxide at the cathode and the oxidation of lead metal at the anode. This is a conproportionation reaction. The products of both the oxidation and reduction half reactions are lead-2 sulfate.
Kind of cool. And again, like I mentioned, when you start the car, it's behaving like a galvanic or voltaic cell, and when you're driving, it's actually behaving like an electrolytic cell.
When a lead storage battery discharges, lead at one electrode is converted into lead-2 sulfate. At the other electrode, lead dioxide is also converted into lead-2 sulfate. The lead sulfate in each case adheres to the underlying electrode. When the current is reversed, electrons transfer from one lead sulfate electrode to the other, and the battery is thereby recharged. If the lead sulfate did not adhere to the electrodes, recharging would be much slower.
And so we can look at reactions, determine if they're spontaneous or non-spontaneous by thinking about the potentials. And so copper ions plus zinc going to copper metal plus zinc. And so we have the reduction of copper as a 0.34. Oxidation of zinc would be a plus 0.76. And so that gives us a positive potential. And so E naught is positive, delta G would actually be negative. And so we could actually use that for a galvanic or voltaic cell. Now, there's actually a special short time notation for cells. And so here's that zinc copper cell. And so the electrode goes on the outside. And so zinc is the electrode, copper metal is the electrode. So those on the outside. We have a single line that represents boundary between phases. And so zinc's a solid, zinc ions in a solution. So we have a single line. And then we have a double line for the salt bridge. Now the layout for the cell notation actually corresponds to physical proximity. And so we want the copper ions next to the copper metal because they actually touch physically when you build the cell. It is not related to the order that you see it in the final reaction. Now you can also include conditions like concentrations after the compounds. Now this is a slightly different cell. One question would be, is platinum part of the net reaction or part of either oxidation or reduction half reactions? And the answer would be no. Platinum is just the electrode where the reaction is going to occur. Again, remember, platinum is used often for electrode, and sometimes it does not involve in the reaction. It's fairly unreactive. And so here, the oxidation is always on the left in terms of cell notation, and so the oxidation is going between the cerium 3+ and cerium 4+. The platinum is just the electrode. It is not part of the reaction. And so this is what that reaction looks like. We have the oxidation, half reaction, reduction, half reaction, the net reaction, and that potential is plus 1.26. Now, if you want to determine the reaction from the potential, you have to always remember that on the left-hand side is oxidation, on the right-hand side is reduction. So you determine the oxidation, reduction, half reactions, you look at the corresponding potentials, you add the potentials to determine the potential of the cell, and if the potential is positive, then it's going to be a galvanic or voltaic cell. If the potential is negative, then it's going to be an electrolytic cell. So please remember, electrochemical cells are cool. They can be used to convert chemical potential energy into electrical energy, or electrical energy into chemical potential energy. The chemistry in an electrolytic cell is exactly the same as occurs in a single beaker. And so it looks kind of complex having those two beakers, the salt bridge, the electrodes. But again, the chemistry is the same if you have those two beakers or if you have a single beaker. I hope that was helpful.